In this video, we're going to discuss solubility equilibrium. So most ionic compounds are soluble, at least to some extent, in water. A compound that is said to be soluble means that you can dissolve a large amount of that substance in a given volume of water. Whereas a compound that is insoluble, that means that only a very small amount of that substance will dissolve in a given volume of water. So let's say that we take a small amount of an ionic compound and add it to a certain volume of water. It will be soluble and it will dissociate or break apart into its component ions. So let's use this as an example. Let's look at calcium fluoride. If we took calcium fluoride, solid, and we dissolved it in water, at least a little bit of it, we would get it dissociating into calcium and fluoride ions. So let's say we took our calcium fluoride and we put a small amount of it in our water. It would dissociate, so it would break apart into its component ions. If we continue to add the calcium fluoride to the same water, eventually we'll get to the point where the water can no longer solubilize or hold any more ions. At this point, the solution is said to be saturated. So let's say we continued adding the solid calcium fluoride to our compound, to our water. Eventually, as we said, the water can no longer hold anymore, and so it will begin to just precipitate or settle down to the bottom. So we'll get the solid phase. This is supposed to be an S here, settling at the bottom, and we'll have a certain fixed concentration of ions in our water. If we add more of our compound, it won't dissolve, but it will continue to precipitate out. So we've got a saturated solution, but we continue to add calcium fluoride, it will only sink to the bottom. The water cannot hold any more ions once it's saturated. Now, in a saturated solution, a dynamic equilibrium exists between our solid phase down here at the bottom and the ion or the aqueous species, the dissolved ions. So we end up having a dynamic equilibrium between the two phases once we have a saturated solution. The solids continue to dissolve and form the ions, and the ions will continue to come together and form the solid. And the rate of the dissolution and the rate of the precipitation are equal. So the rate at which the ions precipitate and the rate at which our solid dissociates becomes equal. So again, in a saturated solution, we have a dynamic equilibrium that exists between our aqueous and our solid phases. So since the solid compound, the undissociated compound, and the ions are in equilibrium, we should be able to write an equilibrium expression. So let's take a look here. Here's our chemical formula for the dissociation of calcium fluoride in water. If you would, pause the video and see if you can write an equilibrium expression for this chemical equation. So it should look something like this. Here we have, let's say this is Kc, because that's our equilibrium constant. We'll mention the Sp in a second. But Kc is equal to the concentration of our products divided by the concentration of our reactants. But remember, anything in the solid phase, we leave out of our equilibrium expression. So our equilibrium expression is simply the equilibrium constant is equal to the concentration of our calcium times the concentration of our fluoride, and we square it since we have a 2 coefficient here. Now, since this is an equilibrium constant, but since we're talking about solubility, instead of Kc, we give it a Ksp to indicate solubility product. So this is the equilibrium constant when we're talking about a solubility expression. So in general, the expression follows this form. Here we have our ionic compound, and here we have our ions with some coefficient here and some charge, and some coefficient and some charge. The solubility product constant, Ksp, would equal an expression that would look like this. So pause the video for a second. Be sure you write that expression down. Now let's take a look at a problem involving solubility product constants. We have a saturated solution, and again, in order for equilibrium to exist, the solution must be saturated. So we have a saturated solution of calcium fluoride is prepared. The concentration of calcium and fluoride are measured at equilibrium, and we're shown to have a calcium concentration as follows and a fluoride concentration as follows. Calculate KSP for this calcium fluoride solution. Okay. Well, we know that our chemical equation to show the dissociation of calcium fluoride would look like this. For every 1 mole of calcium fluoride that dissociates, we get 1 mole of calcium and 2 moles of fluoride. Then we could write a KSP expression, which would look like this. Now all we have to do is just plug in our values. We're given the concentrations, equilibrium concentrations of calcium and fluoride. So we plug those in and solve for KSP, and we get a value of 1.5 times 10 to the minus 10 for our KSP. Okay, let's take a look at another similar problem. We want to calculate the KSP for silver phosphate, and we're given the equilibrium concentrations for the silver and the phosphate ions. Calculate KSP. Pause the video and see if you can do this one. So the first thing we want to do is write our dissociation equation for silver phosphate. 1 mole of silver phosphate, when it dissociates, will produce 3 moles of silver ions and 1 mole of phosphate ions. We should be able to write a KSP expression, an equilibrium expression, which would equal the concentration of silver cubed times the concentration of phosphate to the first. Now all we have to do is plug in our values, which are given, and solve for KSP. And you see we get 1.8 times 10 to the minus 18. So the solubility product constant can be used to compare the solubility of various ionic compounds. The smaller the numeric value of our KSP, the lower the solubility of the compound, and vice versa. The bigger the KSP, the more soluble the compound is. If we look back at our calcium fluoride, remember, here's our KSP expression. So the more soluble a compound is, the more ions it produces. So for every 1 mole, or however much we dissolve of our solid, the more soluble it is, the more ions we get. So the larger these values will be in our KSP expression. So the more soluble an ionic compound is, the larger the KSP. If these values are very small when a compound is dissolved in water, then our KSP will be very small, indicating that it's not very soluble. So KSP values give us some idea of the solubility of various ionic compounds. You can see here is a fairly large table of a lot of different KSP values for different compounds. And you range from things that are relatively soluble to maybe something like bismuth sulfide with a value of 1.6 times 10 to the minus 72, which is incredibly insoluble. But nonetheless, you will still have, no matter how insoluble, a very small amount will still dissolve into ions or dissociate into ions when put in water. So there's another term that we want to be familiar with, and that's molar solubility. The molar solubility is the number of moles of a substance, generally our ionic compound, that can dissolve in 1 liter of solution before the solution becomes saturated. So in order to illustrate this molar solubility, let's take a look at a problem. Here we're asked to calculate the molar solubility for silver chloride, and we're given the KSP value. So to solve a problem like this, the first thing you would want to do is write the dissociation equation. Silver chloride, 1 mole of silver chloride solid, will produce 1 mole of silver ions and 1 mole of chloride ions. Next thing we want to do is, since this is an equilibrium issue, we want to set up an ice table. Here we have set up an ice table. Our initial concentration of silver chloride, well, this is not applicable since it's a solid, but our initial concentration of silver would be 0. Initial concentration of chloride ions would be 0. But as our silver chloride begins to dissociate, the silver chloride will be plus X, chloride will be plus X, so our equilibrium concentration will be X and X. Now the next thing we should do is we could write an equilibrium constant expression, a KSP expression for this equation. And the KSP would be equal to the concentration of silver to the first times the concentration of chloride to the first. Now we can plug in our equilibrium values, in for silver and in for chloride. And we get our KSP, which is given here in the formula, 1.6 times 10 to the minus 10, is equal to X times X, or X squared. And if we solve for X, we get X equal to 1.3 times 10 to the minus 5 molar. So what that tells us is that X, that's the molar solubility. So for silver chloride, we can dissolve 1.3 times 10 to the minus 5 moles of silver chloride in 1 liter before we have a saturated solution. Now we can also use that to calculate the equilibrium concentrations of silver and chloride. Since those are X, our equilibrium concentration of silver would be 1.3 times 10 to the minus 5. And our concentration of chloride at equilibrium would also be 1.3 times 10 to the minus 5 molar. Okay. So let's work several more of these. Let me show you the question. Pause the video after each question and give it a try, and then I'll solve it with you. Okay, so let's first thing write our equilibrium, our dissociation equation. We can set up an ice table here. Now pay attention to your stoichiometry. For every 1 mole of silver chromate, we get 2 moles of silver and 1 mole of chromate. So we're going to start off initially at 0. Our silver change is going to be plus 2x, since we have a 2 here, and our chromate will be just x. So our equilibrium concentrations will be 2x and x. Now we can write our KSP expression. Again, don't forget to square the silver. Plug in our equilibrium concentrations for silver and for chromate. And our KSP value is given. So we have 9.0 times 10 to the minus 12 is equal to 2x squared times x, which gives us 4x cubed. Solve for x, and we get an x value of 1.3 times 10 to the minus 4 molar. So that means that for silver chromate, our molar solubility is 1.3 times 10 to the minus 4. It's always equal to x. So that means we can dissolve 1.3 times 10 to the minus 4 moles of silver chromate rather, in 1 liter of water. Now we can also use x to calculate the equilibrium concentrations of silver and chromate. Remember, our silver is 2x, so we multiply this times 2 to get the concentration of silver at equilibrium, and chromate will just be equal to x. All right, now pause the video and give this one a try. So let's write our dissociation equation, set up our ice table, set up our KSP expression, plug in our equilibrium values, and solve for x. So x is equal to our molar solubility. Our concentration of calcium is the same, and our concentration of iodate ion would be twice that. So let's try a few more. Pause the video here. Okay, so let's write our dissociation equation, set up our ice table, our KSP expression, plug in our equilibrium values, solve for x. X gives us our molar solubility. Our concentration of magnesium is equal to that of our molar solubility, and the concentration at equilibrium of hydroxide would be twice that. Okay, pause the video again, give this one a try. Okay, so here's our dissociation equation. We set up our ice table, our KSP expression, plug in our equilibrium values, and solve for x. So our molar solubility for chromium hydroxide, chromium 3 hydroxide, is what you can see here. Our concentration of chromium would be equal to that, and the concentration of hydroxide at equilibrium would be 3 times that. Let's do one last one. Okay, Pause the video here. Okay. Let's write our dissociation equation for calcium phosphate. Set up our ICE table. Again, be careful of your stoichiometry. Set up a KSP expression. Plug in your equilibrium values. Solve for X. And X will be equal to the molar solubility of calcium phosphate. Now our concentration of calcium is going to be 3 times the molar solubility, and the concentration of phosphate will be twice that. So practice some of these videos. Be sure you appreciate how to solve for molar solubility as well as KSP when you're asked, and be able to write a KSP expression for the dissociation of any ionic compound.